So we're going to look at Unit 2 exam review for AP Pre-Calculus, and that covers chapters 4 and 5. So we're looking at exponential functions, logarithmic functions, sequences, and how it all connects. So we're going to start with the basics of exponential functions. So we have 4 different scenarios. Our template for exponential functions is a times b to the power of x. So b is the thing that has the exponent on it. So when a is positive and when b is greater than 1, this right here is letting us know that we have exponential growth. And so an example I give you, this would be an asymptote. And then because we're seeing growth, our graph will look something like that. For the next one, a is still positive and b is less than 1 this time. So the example shows like 0.5 with the exponent on it. It could be a fraction like 2/3, 1/2, 1/4. This demonstrates exponential decay. And so I still have an asymptote on my x-axis, but because I'm decaying, it's going to kind of flatten out by that asymptote. The next two we're looking at, we have b is greater than 1 and b is less than 1, but the difference is now our a value is negative. So when I have a negative a value, that's the number out in front, I can kind of think back to transformations. This negative is causing a reflection over my x-axis. So instead of my graph being up here, it's going to be in my bottom 2 quadrants there. So b is still greater than 1, so I would start it as exponential growth, but that doesn't take into account the negative. And so with the negative, I'm reflecting it over the x-axis. Now my graph will look like that. So it's like this first one, and I just flipped it. Then for the last one, same thing. Since it's negative, I do have a reflection. And then because it's very similar to this one, I'm taking this graph and I'm reflecting it over my x-axis, and so my graph will look something like this. And so a function is exponential if the outputs change proportionally as the input values increase in equal length intervals. So this inputs in equal length intervals could be like 1, 2, 3, 4. They're all 1 apart. It could be 2, 4, 6, 8, as long as they're equally spaced. And then we also talked about in class how inputs change additively as outputs change multiplicatively. And then one thing about exponential functions is there's either going to be concave up, so this is concave up, this is concave up, and then this is concave down, concave down. And so there's no inflection points because by definition, an inflection point is when our concavity switches. And so if we only have concave up or concave down, it never switches, which means there's no inflection points. Into our next box, we're going to look at sequences. So we have arithmetic sequences, which we kind of think of like a linear function. And we have the template here. So I have a sub n, where this right here, a sub k, is just my kth term. And then I'll give you an example. This d is our common difference. So what are we adding by each time, subtracting by each time? And then this k relates back to the a sub k. So for example, if in my sequence I had a common difference of adding 2 and my second term was 10, I would have a sub n equals 10 plus my common difference of 2, and then n minus 2 because I said my second term was 10 with a common difference of 2. For a geometric sequence, they behave like exponential functions. So this g sub k is my kth term, where it connects to the k and the exponent. And then r is our common ratio. Then we're going to look at exponent rules. So if I am multiplying two terms with the same base, I want to add my exponents. So this would become b to the power of k plus m. When I have a power raised to another power, I want to multiply my exponents. So the two exponents are smushed together to demonstrate that multiplication. When I have a negative exponent, I have to move it to where it currently isn't at. So this negative exponent is causing b to move into our denominator. The exponent goes with it, and as soon as it moves, it's not negative anymore, it turns positive. And then whatever my coefficient is, whatever did not move into my denominator, will stay in my numerator. So my invisible coefficient is 1, so I have 1 over b to the power of positive k. And then this one here, if I'm dividing two terms with the same base, I want to subtract my exponents. I always have to do the top minus the bottom because order matters for subtraction. If I have an exponent that's a fraction, I can identify the denominator here is my index. So my m is telling me like what root it is. Is it a square root? Is it a cubed root? And then the numerator of that fraction goes on the inside. So I'll give you an example for this one. If we had b to the power of 2/3, that would become the cubed root of b squared. And then that last exponent rule, anything to the power of 0 is 1. On the last part of this page, we're looking at properties of logarithms, which logarithms are connected to our exponent rules. Since logarithms and exponentials are inverses of each other, they are connected. So one thing I do want to mention about logarithms is we cannot take the log of a negative number. That is not possible. And I'm actually going to start with this one right here to connect back to why it's not possible to take the log of a negative number. But if we have log base b of c equals a, I can convert this into exponential. The base of my log becomes the base of my exponential. And then I can do my little cloud. So b to the power of a equals c. So b to the power of a equals c. How I also remember it is, yes, the bases are the same, and then b and c are so close in the logarithmic form, they cannot be close in my exponential form. So c would not be the exponent on b because they're so close here. It has to be a as the exponent, and then c is way over here. So the reason that we cannot take log of a negative number is if c is negative, this would not make sense. There is nothing that I can raise to an exponent that will produce a negative number. So if I had 2 as my base and I'm trying to square it or do a negative exponent, that would only give me a fraction. It doesn't give me a negative c. I also can't have a negative base of my log, which connects here. So then let's look at the other ones. If I have a log with an exponent, here I can move that in front and that'll become my coefficient and vice versa. So this would become m times log base b of x. And so if I started off with this one, I could move my m to an exponent to get my original. If I have multiplication inside of a log, that will turn into addition between two logs. So I would have log base b of x plus log base b of y. And then vice versa, if I start out with this, I can condense it into this. Log base b of x divided by y would turn into log base b of x minus log base b of y. When I have a log without a base noted, we know there is an invisible 10. So that would be log base 10 of x. And then a natural log has an invisible base e. So I have seen it written both ways. Either way, we have a base e on a natural log. For our change of base formula, if I have log base b of x, I can rewrite that as log of a different base, so that's why it's base a now, of x, divided by log base a of b, where b was my original base. And so I can make a whatever base I want. And we are going to do an example at the bottom to kind of demonstrate that and how that would be useful. In class, we did default to a base 10, but there is a reason why we should use this if we're not allowed to use a calculator, and we'll go through an example at the bottom here. So a couple of these examples you can try on your own. I'm going to go through them pretty quickly. If I have an exponent of 1/2, that'll be the square root of 9, which is 3. So if I have an exponent of -1/2, I know it'll turn into 1 over the square root of 9, because that negative exponent pushes it into my denominator, which I can then simplify into 1/3. Again, a negative exponent means it's moving to my denominator. Once it's in my denominator, it is a positive exponent. 1 over 2 to the third is 1/8. For our bottom row, log base 4 of 16 is equal to something. So if we think about converting it into exponential, 4 to what exponent would give us 16? Well, I know it has to be 2, because 4 squared is equal to 16. So here, log base 9 of 3 equals something. So 9 to what power equals 3? So sorry about that little error there. Well, I know the square root of 9 is 3, and how I denote a square root as an exponent would be 1/2. So log base 9 of 3 is 1/2. This last one here, log base 4 of 8 equals something. 4 to what power gives us 8? Well, I know 4 to the power of 1 is 4, and 4 squared is 16. So I'm going to have like a fraction or a decimal as an exponent. So this is where I want to use my change of base, and I'm not going to use my calculator. I know 4 and 8 both can be represented as 2 to some exponent. So I'm going to choose a new base of 2. So when I rewrite this, I'm going to have log base 2 of 8 divided by log base 2 of 4. And so now I can figure out each separately. So just my numerator, log base 2 of 8 is 3, because 2 to the power of 3 is 8. And then my denominator, log base 2 of 4, would be 2, because 2 squared, or 2 to the power of 2, is 4. And so log base 4 of 8 is equivalent to 3/2. That is where we're going to pause for part 1, but you can watch the other parts for the rest of the recap notes.